center of curvature, radius of curvature, focus and the focal length for spherical mirror. Let this is the concave mirror in which this is the principal axis and this point is known as the pole, and let this is the convex mirror in which this is the principal axis and this is the pole. And what is center of curvature? And here if you join, you find here this is a sphere and this is the center of the sphere. So center of curvature is a point on the principal axis for which the lens forms a part. That is the center of curvature, or simply it is the center, and the distance from the center C to the pole is known as radius of curvature R. Like for convex mirror, this is a sphere from which the mirror forms a part, and this is the center of the sphere. So let this is C, and the distance between the center of curvature and the pole is known as the radius of curvature. And you can say, by using the sign convention, what will be the radius of curvature for concave mirror? Yes, the radius of curvature will be negative as it lies left to the pole. So this is negative. And for this is a convex mirror. For the convex mirror, by using the sign convention, we can say the radius of curvature will be positive because it lies right to the pole. That's why it will be positive, and for concave mirror it will be negative. Then if you imagine a ray of light comes from infinity, and when the ray of light that comes from infinity, you have to take they are parallel to the principal axis. So these two rays that comes from infinity, so they are parallel to the principal axis, and after reflection through the mirror, they will pass through a point. Clear? They pass through a point, and the point through which they pass is known as focus F. That means we can say the ray of light which are parallel to the principal axis, after reflection through the mirror, they pass through the focus, and the distance between the focus and the pole is known as the focal length. And here also they will the rays which comes from infinity, they are parallel to the principal axis, and after reflection through the mirror, they will pass through the focus. So the distance between the pole and the focus is known as the focal length. And again we can say by using the sign convention, the focal length for convex mirror is positive and the focal length for the concave mirror is negative. Clear? This is about the center of curvature, radius of curvature, focus and focal length. Clear? And next we have to find out the relation between F and R. Relation between focal length F and radius of curvature. Clear? So first we have to draw the diagram. This is for the concave mirror. This is the principal axis and the ray of light, the parallel to the principal axis, after reflection through the mirror, they pass through the focus. So this is F, and you have to remember the ray of light which pass through the center of curvature C, that is undeviated. Clear? Here this is the center of curvature and the ray of light which passes through the center of curvature, that is undeviated, and it will act as the normal to the surface. As this is the incident ray, this is the reflected ray, we can say this angle is angle of incidence and this is angle of reflection, and from laws of reflection we know the angle of incidence is equal to the angle of reflection. So this is theta, let this is theta and this is theta. Clear? And in optics always you have to take the aperture should be small. That means this aperture should be small. Suppose this is the aperture, and if you choose a small aperture from here, it will be a plane, not a curved surface. That means if you let this point is M, this is P, and you have to draw a perpendicular, let this is X. That means for smaller aperture, in optics always you have to use small aperture. For small aperture, this curved surface will be a plane surface. That means for smaller aperture, P and X will be lie in a single point. They are a single point. X coincide with P. So here these two rays, this ray and the principal axis, they are parallel to each other, and this intersect the two rays. That's why this angle theta will be equals to theta, and the total angle is twice of theta. Again this ray and the principal axis, they are parallel to each other, this ray intersect, then this angle will be equals to this angle, 2 theta. Clear? This is for concave mirror, and the same thing you can calculate for convex. This is the convex mirror, this is the principal axis, these are the rays, this is P and it will get reflected and it appears to pass through focus. And another ray that passes through the center of curvature that moves undeviated. That means this is the ray that passes through the center of curvature, which will act as the normal to the surface. And from a laws of reflection, we know the angle of incidence is equal to the angle of reflection. Then we can take theta. So the total is twice of theta. And again, this ray and the principal axis, they are parallel to each other, and this line intersect. So this angle will be theta. And these two are parallel. This line intersect. This angle is 2 theta. So this will be 2 theta. Clear that this point is M, and you take this is N normal to the principal axis. And for smaller aperture, P and this is X. P and X coincide. X coincide with P. So this is for concave mirror and this is for convex mirror. And from the diagram, in the triangle MCX, in triangle MCX, what will be tan theta? Tan theta is mx divided by cx, mx divided by cx. And again in triangle MFX, tan of twice of theta, tan of 2 theta, that is equals to mx divided by fx. Clear? Here also tan theta is equals to mx divided by cx, and tan of 2 theta, that is equals to mx divided by fx. Clear? And we know for smaller angle, tan theta, that is equals to nearly equals to theta. And here tan theta is, so that is equals to mx divided by cx, like tan 2 theta, that is nearly equals to 2 theta, that is equals to mx divided by fx. So we can write, so mx divided by fx, that is twice of theta. Value of theta is mx divided by cx. So we can write that is twice of mx divided by cx. So from both sides mx will be cancelled. That implies fx will be equals to cx divided by 2. And in the beginning we assume the aperture should be small. For smaller aperture, so you can write here, for smaller aperture x lies on point P. So you can write Fx that is equals to Fp. Fx that is equals to Fp, and Cx is equals to Cp, and Cx that is Cp. So in place of Fx we have to write Fp, that implies Fp that is Cp divided by 2. So what is Cp? The distance Cp, that is the distance between the center of curvature and the pole. That distance is known as the radius of curvature. We have discussed it here. And Fp that is the distance between the focus and the pole, and that distance is known as the focal length. So we can take Fp, that is the focal length. So here Fp, that is the focal length, so we can write Fp is equals to focal length, that is equals to Cp, the distance Cp, that is the radius of curvature R, that is R divided by 2. So this is the relation between the focal length and radius of curvature. So here we can write F, the focal length, that is equals to half of radius of curvature, or we can write the radius of curvature, that is twice of focal length. This is the relation between focal length and radius of curvature. The focal length, that is the half of radius of curvature, and that's why the radius of curvature is twice of focal length. Remember this. This is the relation between focal length and radius of curvature.